today actually we are going to discuss about the transformation of phases. If you remember, in our last two lectures we have discussed about the phase diagram, and then how we are getting the different materials at different temperature. So, in this particular course we are going to discuss about the phase transformations, means we are going to change the material phases from one phase to another, so that we can get the better properties in terms of mechanical properties or maybe the thermal properties or maybe the electrical properties. Sometimes it is required for us from the material scientist point of view that to change the material properties for gaining the materials in a wider applications. So, first we are going to discuss that why we need to study about the phase transformations. Say suppose I am giving you a small example. So, the tensile strength of an iron carbon alloy of eutectoid compositions and be varied between 700 to 2000 megapascal depending on the heat treatment process adopted. So, that means suppose I am having one materials, I am supplying the heat to that materials and the material is changing, or maybe it is segregating from one phase to another phase, and it is giving you the better mechanical properties. This shows the desirable mechanical properties of materials can be obtained as a result of phase transformations using the right heat treatment process. Yes, of course, it should be the proper. It does not mean that every time I can give some heat or maybe I can cool down the materials and the material will give the desired properties. No, there is some specific conditions and it varies from materials to materials physical properties that it can show the better properties. In order to design a heat treatment for some alloy with desired room temperature properties, time and temperature dependencies of some phase transformations can be represented on modified phase diagram. Yes, of course, the material which we are preparing day to day in our labs or maybe in the industry. So, just to increase certain kind of properties we can do the heat treatment process of that particular materials, but we have to know the phase transformations of that materials, that at what temperature, at what pressure the material will behave, or maybe it can give you the better properties. So, first before going to start, let us know what is phase. So, phase is the homogeneous portions of system that has uniform physical and chemical characteristics. It is physically distinct from other phases, chemically homogeneous because the material throughout the whole area or maybe the whole volume it will show you the same properties, and mechanically separable portions of a system. Now, what is phase transformations? Process of formation of a new phase with a distinct physical or chemical character of a different structure than parent phase. Change of one phase into the another. Say simple, we are changing the phase from one, maybe from solid to liquid, or maybe sometimes it may happen from liquid to solid, or maybe sometimes it may happen from solid to solid, or maybe liquid to liquid. So, there are so many types or maybe so many steps are available by which we can change the properties of the material. So, suppose if I give an example, say suppose from water to ice, simple from liquid to solid we are changing its phases. Alpha iron BCC to gamma iron FCC structure, or maybe from gamma iron FCC to alpha iron ferrite plus cementite, which involves changing in compositions, some ferromagnetic phase to paramagnetic phase based on a property. So, sometimes we can change the magnetic properties of that materials also, and this is the things which I also discussed in our last lecture, that suppose if I go directly from the solid to liquid. So, I will go through the melting, and from liquid to solid I will come through the freezing process. Liquid to gas I will go to the vaporization process, and from gas to liquid it will be the condensation process. If I go to solid to gas directly, it is called the sublimation process, and if it is from gas to solid it is called the deposition process. And if I go for the gas to plasma, which is generally we are thinking that it is the fourth state matter or maybe fourth state of any kind of materials. So, direct if I want to go from gas to plasma, it is called the ionization process, and from plasma to gas it is called the deionization process. So, now we have to discuss about the classifications of the phase transformations. So, it is divided into three parts. First one is called the simple diffusion dependent phase transformations, second one is called the complex diffusion dependent phase transformations, and third one is called the diffusion less phase transformations. So, what is simple diffusion dependent phase transformations? So, in that case no change in compositions, no change in phases. Example, melting and solidification of pure metals, grain growth, recrystallization, allotropic transformations. Say suppose I am having any solid metals, in that metals some impurities are there. So, what I am going to do, either I will dissolve it into some solvent or maybe I can heat it and then simple from that I will remove the impurity. So, in this case you can see that from by the sol gel methods we are dissolving in some hot solvent and then after filtering just we are removing the filtrate or maybe the impurities from that particular material. Next is called the complex diffusion dependent phase transformations, where there is no change in phase compositions, only changes in number of phases. Example, the eutectoid transformation. Say suppose I am having the gamma austenite and I am doing the eutectoid transformations over there. So, I am getting two types of phases over there, one is called the cementite, which is nothing but the Fe3C, another one is called the alpha ferrite, and you can distinctly see the crystal structure of these two phases are different. Then we are going to discuss about the diffusionless phase transformations, which produces the metastable phase, involves small displacement of all atoms in structure. Example, martensitic transformations. In this image you can understand that the atom, they are going to shift or maybe they are going to change their places, and due to that some suppling is taking place, some distortion is taking place in this particular point, and some are the undistorted atoms. So, like this way the diffusionless phase transformations is taking place. Now, what are the actual kinetic of phase transformations? So, generally the kinetics is the study of reaction rates of phase transformations. So, phase transformations generally it involves in change in structure and compositions of any kind of materials. It is the rearrangement and redistribution of atoms which requires the diffusion process. So, process of phase transformations involves two things, one is called the nucleations, another one is called the growth. Nucleations is means that it is the initial stage. So, first the material will nucleate, it will start to be born, and then after that that will become bigger and bigger. So, it is like a human's birth type of thing. So, suppose I am having the embryo, then it will be little bit bigger. So, it is like a baby. So, nucleation is taking place, and then from baby to the mature person, that means the growth is taking place. So, nucleations involves the appearance of very small particles or nuclei of a new phase which are capable of growing. So, that means it is the small things in which it is going to grow. Nucleus forms when Gibbs free energy G of system decreases, del G is called here is the negative. Now, growth is the increase in size of nucleus at the expense of parent phases. So, now it has been born and now it will become bigger and bigger. So, here this is known as the nucleations, and then after that the growth has started tremendously, and this is the graph of fraction of transformations versus logarithmic of heating time. Now, there are two types of nucleations, one is called the homogeneous nucleations, another one is called the heterogeneous nucleations. What is homogeneous nucleations? First I will tell you the theory. Nuclei of the new phase form uniformly throughout the parent phase, require supercooling of 80 to 300 degree centigrade. From this image you can understand that at time t1 the nucleations begins, means small particles or maybe the atoms has been formed, and then after that growth and nucleations. So, whatever has formed earlier, that is becoming bigger and bigger, and also some new phases or maybe the new atoms are still forming. So, like this way it is called the homogeneous. So, at last growth and nucleations of the new bubbles is going at higher time also. And when we are talking about the heterogeneous, heterogeneous means nuclei from at structural inhomogeneities, insoluble impurities, grain boundaries and the dislocations, require slight supercooling, it is 0.1 to 10 degree centigrade. So, in this particular case nucleation has started, no new nucleation will be there in future. So, only the growth will be taking place of that existing nucleations. So, no new nucleations, just growth is taking place, and at the higher time also the same thing is happening. Now, we are going to details for the homogeneous nucleations. It occurs when there are no special object inside a phase which can cause the nucleations. It is also called as the self nucleations, require supercooling or superheating for nucleation to occur. So, supercooling and superheating is required. Probability of nucleation is same throughout the volume of the parent phase. What is the example? When a pure liquid metal is cooled slowly because its equilibrium freezing temperature to a sufficient degree, numerous homogeneous nuclei are created by slow moving atom bonding together in a crystalline form. So, in this particular case what happened? So, crystal nucleus is forming, and then after crystal growth is taking place, but still some new atoms are creating, or maybe the bubbles are creating. So, this is the examples of the homogeneous nucleations. Now, we are going to discuss about the solidifications of a metal. So, above melting point like Tm, generally we are giving the notations for the melting temperature. Liquid free energy GL is less than Gs. So, which is called the solid free energy Gs. So, free energy change for solidification del G is greater than 0. So, below melting temperature del G is less than 0 and nuclei of the solid phase form, means it is starting. Two contributions to free energy change: volume free energy, that is del GV, and surface free energy, that is gamma, due to creation of a new surface. Taking nucleus as a spherical particle of radius r. So, in this particular case, this is the formation is taking place, nucleation has started. So, suppose this is the atom and we are taking its radius as a r. So, this is the solid liquid interface and the rest of the area is the liquid one. So, del G is equal to 4 by 3 pi r cube del GV plus 4 pi r square gamma. Tiny particle of solid that forms first will be stable only when it achieves a critical radius r prime. Below the critical radius it is unstable and it is called the embryo. That means it has been started and then this radius is not stable. After certain time it will achieve the stable radius, or maybe the stable shape, or maybe the size. Since this happens at the maximum of the del G versus r curve, so d upon del G by dr is equal to 4 by 3 pi del GV into 3 r square plus 4 pi gamma into 2 r is equal to 0. This yields r prime is equal to 2 gamma by del GV, and del G prime is equal to 16 pi gamma cube by 3 del GV square. So, now we are going to discuss about the heterogeneous nucleations. So, already I told that in the heterogeneous nucleations no new nucleation will be taking place, only whatever the nucleations has already been done in earlier, the growth will be only taking place. So, in this case nucleations occur at the interface between two phases or at the grain boundary. Probability of nucleations is much higher at certain preferred sites such as mold wall, inclusions, grain boundaries compared to the rest of the parent phase. Example: solidification of a liquid on an inclusion surface. So, suppose we are having that liquid and solid, and then this surface is known as the gamma IS, which is nothing but the solid surface, and gamma IL, which is nothing but the liquid surface, and gamma SL, which is called the solid and liquid surface, is this one. So, now it has three interfacial energies that exist at two phases boundaries. Theta is wetting angle formed between the gamma SL and gamma SL vector. So, generally we are doing it by the contact angle measurement. So, surface tension force balance in the plane of flat surface is given by gamma IL is equal to gamma IS plus gamma SL cos theta. With a similar approach, it can be shown that r prime is equal to minus 2 gamma SL by del GV, and del G prime is equal to 16 pi gamma cube SL by 3 delta GV square into S theta. So, the small value of theta ensures that the energy barrier del G is effectively lowered in heterogeneous nucleations. So, now nucleation and the growth kinetics. Growth, it is the increase in size of nucleus at the expense of parent phase. Growth rate G is determined by the rate of diffusions and its temperature dependence is same as for diffusion coefficient. So, G is equal to C exponential of minus Q by KT. Once the embryo exceeds the critical size r prime, which I have already told that critical diameter, when it will cross, growth of nucleus starts and nucleation continues simultaneously. Nucleation and growth rates are function of temperature. That means, all the embryo is not going to be born. So, it should first reach the critical diameter or maybe the critical radius, and then after that the nucleation or maybe the grain growth will be taking place. Nucleation rate increases with cooling rate and degree of undercooling. That means, del T is equal to Tm minus T, Tm is the melting temperature. High nucleation rate and low growth gives the finer grain size. So, what is the consequence? Overall transformation rate means product of nucleations and the growth rates. So, here is the graph, that is temperature into the y axis and the rate into the x axis, and you can see that this is the nucleation rate, this is the growth, and this is the melting temperature of that materials, and this is the overall transformation rate, which is nothing but the product of this nucleation rate and the growth rates. Now, we are going to discuss about the rate of phase transformations. So, transformations follow a characteristics S shaped or maybe the sigmoidal curve. So, modeled by the Avrami equations, which is known as the y is equal to 1 minus exponential of minus k t to the power n, where k and n are time independent constants. Rate of phase transformations is the reciprocal of time for transformation to proceed halfway to completions, which is r prime is equal to 1 by t 0.5 is equal to a e to the power minus q by r t, that is known as the Arrhenius expressions, where r is the gas constant, a is the Arrhenius constant, q is the activation energy, and the t is the temperature, absolute temperature, that is in Kelvin. Rate increase with temperature, rate is often small, so equilibrium is not possible. So, in this particular case you can see that with the temperature, that how the percent recrystallization is taking place, temperature dependence of transformation rate for copper. So, this is the example. Now, we are going to discuss about the supercooling and the superheating, because supercooling and superheating is having a very high impact on these nucleations or maybe the grain growth. So, crossing a phase boundary on composition temperature phase diagram, phase transformations towards equilibrium state is induced, but transitions to equilibrium structure takes time and transformations is delayed. During cooling, transformation occur at temperature less than the predicted by the phase diagram, that is known as the supercooling, and superheating, during heating transformations occurs at temperature greater than the predicted by the phase diagram, that is known as the superheating. Degree of supercooling and superheating increase with rate of cooling and heating. Driving force to nucleate increase as del T increases. So, small supercooling is the small nucleation rate is few nuclei and large crystals. Large supercooling is the rapid nucleation rate, many nuclei and small crystals. So, metastable states can be formed as result of fast temperature change. Microstructure is strongly affected by the cooling rate. Effect of time on phase transformations is explained during the iron carbon alloy. So, now degree of supercooling del T values for the several methods. Say suppose we take the antimony, it is 135 degree centigrade. Generally copper is required for us because we are widely using the copper, that is 236 degree centigrade, iron is 295 degree centigrade, nickel is 319 degree centigrade, then cobalt is 330 degree centigrade, or maybe the gold is 230 degree centigrade. So, this is the degree of supercooling for various metals. Now we are going to discuss about the famous iron carbon phase diagram. So 5 phases are present in the iron carbon systems. So first is called the alpha ferrite. So alpha ferrite, it is the interstitial solid solution of carbon in BCC iron. Maximum solubility of C is 0.025. After that the C will not be dissolved into that phase. Exist from 273 degree centigrade to 910 degree centigrade. So from this we can get the alpha ferrite, and then we are going to austenite, that is gamma phase. Interstitial solid solution of carbon in FCC iron. Maximum solubility of C is 2.1%. So solubility of carbon has been enhanced. Exist from 910 degree centigrade to 1394 degree centigrade. Then we are having the delta ferrite, solid solution of C in BCC iron. See, just we are changing the temperature, the solubility of carbon is increasing and also the phase of that material is going to be changed. First it was in C in BCC, then C in FCC, and then C in again BCC it is coming. Maximum solubility of C is 0.09, it has been reduced. Exist over temperature of 1394 degree centigrade to 1593 degree centigrade. Again we are moving to cementite, it is the intermetallic compound, C content in Fe3C is 6.67%, and the last one is called the liquid iron carbon solutions. So this is coming in this particular case. So in this particular case you can see there are several things. It is the carbon percentage is 0.0 to 6.67% and temperature is increasing in these directions. So this is into the Fahrenheit and this is into the centigrade scale. So when we are talking about, we are getting so many phases, cementite plus pearlite plus transformed ladeburite. In this zone we are getting the pearlite or maybe the cementite when the carbon varies below 2% and it is almost 0.8 to 2%. It is only the pearlite ferrite. Then we are getting the 910 degree centigrade is up to this case almost. So in this case we can get the austenite plus cementite plus ladeburite, or maybe into the higher carbon percentage we are getting the cementite plus ladeburite. So these all are the different phases. So based on the carbon compositions and based on the temperature we are getting the different phases of iron carbon system. So critical temperatures in the iron carbon systems: eutectoid temperature generally 727 degree centigrade during heating, and cooling is AC1 and AR1, where A for arrest, that means arrest, C for chauffe, that means heating, and R for refoid displacement, that means cooling. At normal rates of heating or cooling, AC1 is greater than is equal to AR1. A2 at 768 degree centigrade is Curie temperature above which iron turns paramagnetic while heating. Temperature corresponding to gamma plus alpha by gamma and gamma plus Fe3C and gamma phase boundaries are function of carbon content represented as A3 and ACm. Eutectic temperature is 1146 degree centigrade and peritectic temperature is 1495 degree centigrade. Now what is the classifications of ferrous alloys based on carbon content? Iron contains less than 0.008 weight% of carbon in alpha ferrite at room temperature, still 0.008, that means 2.14 weight% in carbon, usually less than 1 weight% alpha ferrite, plus Fe3C at room temperature. Cast iron generally carbon percentage varies from 2.14 to 6.7 weight%, usually less than 4.5 weight%. Now phase transformations in iron carbon systems. So it comprises of 3 invariant reactions as peritectic reactions, eutectic reactions and the eutectoid reactions. So in this particular case, delta is the ferrite, gamma iron is known as the austenite, alpha is known as the ferrite, Fe3C is known as cementite, gamma plus Fe3C is known as ladeburite and alpha plus Fe3C is known as pearlite. So what is peritectic reactions at 1495 degree centigrade? So in this particular case, the L is equal to 0.53% C plus delta ferrite 0.0 9% of C, converts into gamma iron austenite which is having 0.17% of C. What is eutectic reactions at 1146 degree centigrade? L for 4.3% of carbon converts into gamma iron, that is 2.1% of carbon, plus Fe3C, that is 6.67% carbon. Eutectic mixture of austenite and cementite is called the ladeburite. Next, compositions right and left of 4.3% are called the hyper and hypoeutectic steels, or maybe known as the cast iron. Eutectoid reactions at 727 degree centigrade. So, gamma 0.8% C converts into alpha 0.025% C plus Fe3C 6.67% of C. Eutectoid mixture of ferrite and cementite is called the pearlite. Compositions right and left of 0.8% are called the hyper and hypoeutectoid steels. Compositions up to 2.1% C are steels and beyond these are cast iron. So, simple, by the presence of carbon with temperature, simple we can get the different materials like stainless steel, like cast iron, like mild steel. So, this can be achievable. Now, we are going into the details that about the microstructures. So, microstructures depend on compositions, that means the carbon content and the heat treatment. Eutectoid steel is having 0.8% carbon will have 100% pearlite at room temperature. Pearlite formed under equilibrium conditions consist of alternate lamellas of ferrite and Fe3C. Hypoeutectoid steels alpha plus pearlite, hypereutectoid steels, that is Fe3C plus pearlite. Hypoeutectic cast irons consist of gamma plus ladeburite below eutectic temperature and pearlite plus Fe3C plus ladeburite at room temperature as the gamma transforms to Fe3C and pearlite at eutectoid temperature. Hypereutectic cast irons will have a structure of Fe3C plus ladeburite. So, from this you can understand that structure of the pearlites where we can find the Fe3C into the dark phases and alpha ferrite is into the light phases. So, when you are getting the optical microscope image, so of the pearlite also, so you can see that this is the hypoeutectoid Fe3C which is green in color and the red in color is that eutectoid Fe3C and alpha phase you are getting into the blue in color. Same thing the microstructure of the hypoeutectoid steel. So, you can get the Fe3C, you can get the pearlite, you can get the proeutectoid alpha, but in this particular case what happened, you can see the grain structure is totally different than the this one when you are talking about the microstructure of the hypereutectoid steel. So, you are getting the proeutectoid Fe3C, eutectoid Fe3C, alpha and the pearlite. So, total the microstructure is changing. Now, we are going to discuss about the isothermal transformation diagram. So, it gives the relation between temperature and the time of phase formations. So, this is the time versus the temperature. So, how the temperature or maybe the transformation is taking place. So, through this graph you can get the time and transformation begins in this particular point, then transformation is taking places and the transformation ends in this particular point, which is nothing but the percent of austenite transformed to the pearlite. So, it is also known as temperature time transformations or maybe the TTT diagram. Normal cooling rate forms the pearlite, higher cooling rate forms the bainite. Size of pearlite or bainite depends on transformation temperature. Martensite forms when steel is cooled below martensite start temperature at much higher cooling rate, so that nose of TTT curve shown in the dotted. So, this dotted line is avoided, the long blue arrow over there. Diffusion rate below Ms is so low that gamma tends to M transformations is a diffusionless process. C content remains the same, means carbon content is not going to be changed. Crystal structure changes from FCC gamma to body centered tetragonal or maybe the BCT in structure. Now, again we are going to discuss about the TTT diagram for the eutectoid iron carbon alloy. So, perlite which is gamma having 0.76 weight percent of C, either we can heating or cooling both at certain conditions. Alpha is 0.022 weight percent carbon plus Fe3C 6.70 weight percent C. So, thickness of ferrite and cementite layers in perlite is 8:1. Absolute layer thickness depends on temperature of the transformation. So, you can see in all these cases the temperature is the vital factor over there. Higher the temperature, thicker the layers. Family of S-shaped curves at different T constructs the TTT diagrams. TTT diagrams are for isothermal transformations. At low temperature, transformation occurs early and grain growth is reduced. At compositions other than eutectoid, a pro-eutectoid phase ferrite or cementite coexist with perlite. So, in this particular case, in these regions you can see that there are several structures are present over there when the austenite to perlite transformation is taking place. So, this is the temperature versus the time diagram over there. So, with temperature and with time how the material is changing. So, coarse perlite tends to form at higher temperature, that is relatively soft. Fine perlite which is forming at lower temperature, which is relatively hard in nature. Now, formation of the Bainite microstructure. If transformation temperature is low enough, that is less than 540 degrees centigrade, Bainite rather than fine perlite forms. For temperature 300 to 540 degrees centigrade, upper Bainite consists of needles of ferrites separated by long cementite particles. For T more than equal to 200 to 300 degrees centigrade, lower Bainite consists of thin plates of ferrite containing very fine rods or blades of cementite. In Bainite region, transformation rate is controlled by microstructure growth, that means diffusion rather than the nucleation. Since diffusion is slow at low temperature, this phase has a very fine microscopic microstructure. Perlite and Bainite transformations are competitive. Transformation between perlite and Bainite not possible without first reheating to form the austenite. So, this is known as the upper Bainite structure, where we can see the martensite, cementite and the ferrite, and this is the lower Bainite where we can see the martensite is looks like this, cementite is into the in these shapes and ferrite is into this confinement. Now, we are going to discuss about the spheroidite. So, annealing of perlite or Bainite microstructures at elevated temperature just below the eutectoid leads to the formation of new microstructure which is known as the spheroidite. Spheroidite are spheres of cementite in ferrite matrix. Composition or relative amounts of ferrite and cementite are not changing in these transformations. Only shape of cementite inclusions is changing. Transformation proceeds by composition diffusion, needs high temperature. Driving force for the transformation, reduction in total ferrite, that means cementite boundary area. So, this is the photo micrograph of steel with spheroidite structure. Now, we are going to discuss about the martensite. So, martensite forms when the austenite is rapidly cooled or maybe the quenched. That means, we are raising the material up to high temperature and then suddenly we are dipping that materials into some water or maybe some oil to do the quenching to room temperature. So, suddenly from high temperature the material is coming to the low temperature or maybe the room temperature. Austenite martensite does not involve diffusion, no thermal activations is needed. This is called an athermal transformations. Martensite grains nucleate and grow at a very rapid rate, the velocity of sound within the austenite matrix. Transformation of FCC to BCT, body centered tetragonal, how it is taking place, that gamma FCC 0.8% of carbon, just we are doing the quench, we are getting the alpha prime BCT. So, the carbon percentage is not going to be changed. So, martensite, the properties are metastable in nature, coexist with other phases in iron carbon systems, non equilibrium single phase, occurs instantaneously, that is time dependent. So, this is the micrograph or maybe the color micrograph of the martensite structure. Now, how it is changing from austenite to martensite? That means nothing, only the volume is going to be increased, because we are heating that materials and suddenly we are cooling down the materials. So, generally 4.3% of volume is increasing at that particular conditions. So, in this case you can see the martensite region is this zone, and then after that we are having the bentonite, then austenite, then pearlite, then again austenite, and this is the eutectoid temperature of that particular materials, that is nothing but the 727 degrees centigrade. So, in this particular case you can see that at lower temperature, because I told that from higher temperature to lower temperature the martensite formation will be taking place. So, at lower temperature we are getting, so at more than 200 degrees centigrade the martensite start, below that the martensite is 50% and it is just above the 100 degree or maybe 120 degree, then martensite is 90% are present over there, and this zone is martensite plus austenite. So, this is totally time dependent and the temperature dependent over there. In this particular case you can understand that only the changing, because some atoms over here, that is C along the carbon along the C axis obstructs the contractions. So, just only the volume expansion is taking place in this particular case when we are changing it from the austenite to martensite. Now, there is another famous graphs which is known as the continuous cooling transformations or maybe the CCT diagram. So, generally the CCT curve which is in blue in nature and your dotted is the or maybe the dashed curve is the TTT curve. As CCT occurs at lower temperature and longer time compared isothermal holding, bainite does not form in stills during continuous cooling and CCT curve ceases just below the nose. Microstructure fine or coarse depends on cooling rate, higher the cooling rate finer is the microstructure. So, finite size pearlite is called sorbite and very fine size pearlite is called the trustite. Critical cooling rate is one at which cooling curve just touches the nose of CCT curve. Cooling rate higher than critical rate is needed to form the martensite. So, it is the superimpositions of the isothermal and CCT diagram for the eutectoid iron carbon alloy. So, sometimes some cases like critical cooling rate is one at which the cooling curve just touches the nose of CCT curve. So, in this particular case it is going to touch. Now, next one is called the tempered martensite. So, martensite is brittle, needs to be modified for practical applications. It is done by heating, that is 250 to 650 degrees centigrade for some time tempering, which produces the tempered martensite. Martensite which is BCT and single phase converts into the tempered martensite, that is alpha plus Fe3C phases. Fe3C is nothing but the cementite. Tempered martensite fine grained dispersed cementite grains in ferrite matrix. So, this is the electron micrograph of the tempered martensite, where you can find the fine grain, this small grain of the cementite are present inside the matrix. It is less strong as compared to regular martensite, has enhanced the ductility, ferrite phase is ductile over here. So, elasticity kind of things we can get it from over from here, it is not brittle in nature. Mechanical properties depend upon cementite particles size, fewer, larger particles means less boundary area and softer more ductile material, eventual limit is spheroidite. Particle size increases with higher temperature and longer time, that means more carbon diffusion is taking place, therefore softer and more ductile in nature. So, when we are talking about the hardness, so this is the time. So, when we are talking about the higher temperature and time, spheroidite is becoming softer because its hardness is going down, and this is the tempered martensite, that means at higher temperature it is becoming softer. Now, possible austenite transformations, there are so many possible ways for the austenite transformations. So, first is that austenite, then if you do the slow cooling over there, it will become pearlite and the pro-eutectoid phase. If you do the moderate cooling, then you will find the bainite in structure. If you do the rapid quench, as I told already, you are getting the martensite, and then if you reheat the martensite, you can get the tempered martensite over there. So, solid lines, these solid lines which is known as the diffusional transformations, and these dashed lines is known as the diffusionless martensite transformations. So, if we talk about the strength, so strength is maximum for the martensite and very less for the spheroidite, and of course, it is the vice versa or maybe the opposite for the ductility one. So, for martensite the ductility is very less, and for spheroidite the ductility is maximum. So, now microstructure and mechanical properties for iron carbon alloys. So, this is a overall comparison table. So, micro constituents like spheroidite, phases present is alpha ferrite plus Fe3C. Arrangement of phases relatively small Fe3C sphere like particles in an alpha ferrite matrix. Mechanical properties, it is soft and ductile. So, like this way just we have summarized all these for the spheroidite, coarse pearlite, fine pearlite, bainite, tempered martensite and the martensite. So, for martensite it is having the body centered tetragonal BCT, it is single phase, needle shaped grains generally it is showing, it is very hard and very brittle because sometimes it is having the tempered martensite or maybe the normal martensite. So, now we have reached to the last slide of this particular lecture. So, we have to summarize the whole lecture. So, in this particular lecture we have discussed about the phase transformations, which is the process of formations of the new phases, which involves the two process, generally one is the nucleations, another one is the growth. Abrami equations is used here for the calculation of degree of progress of transformation phases, which is a function of time. During cooling, transformations occurs at temperature less than predicted by phase diagram called as supercooling. TTT diagram is called the temperature time transformation plot. Depending on the type of transitions, it shows various types of complexity. So, simple, in this lecture we have seen that changing the temperature, changing the time, how the material same composition is behaving or maybe the showing the different phases and the different physical properties. Thank you.